Welcome back. 'Tis the season for parametric equations. In many, many previous courses, you have become very familiar with graphs of this form. That is, graphs of functions y equals f of x. But these things have some severe shortcomings. In particular, if y is a function of x, then for any given x value, there can only be one given y value, which means that the graphs of functions are restricted to graphs that are never cut by a vertical line more than once. Well, neither nature nor geometry feel compelled to give us curves that conform to this simple pattern. Is there really no hope of following, say, the path of a bug on a window pane, which might look something like this? That is definitely not the graph of a function. Or for that matter, suppose we have a fly buzzing around three-dimensional space, where we have an x-axis, a y-axis, and a z-axis. And if his motion looks something like this crazy thing, do we just have to throw up our hands and say we are helpless in the face of any curve that does not look like this? No, of course not. We can cope with such situations, and our main tool for doing so is the topic we will be discussing today, parametric equations. The idea is simple. Instead of having a single equation, like y equals f of x, where the y-coordinate of every point is determined by the x-coordinate, we let each coordinate be independent of one another. And instead of saying that a y value must be determined by x, so that once an x value is given, there's no question about the y value. It gets dragged along for the ride with no will of its own. Instead of this kind of situation, which holds in the y equals f of x case, we're going to consider x and y independently of one another, which is why I'm thinking of them on the same level here. And instead, we're going to assume that each of them depends on some third variable, which we most frequently call t, although in other situations it makes sense to use different values for the parameter. For example, whether you know it or not, you've already used parametric equations. You used them in trigonometry. It's funny how everything seems to come back to trigonometry in this class. The unit circle obviously is not the graph of a function, because given one value of x, there are two values of y that correspond to it. So we can't just express this as the graph of a function, y equals f of x. We can, however, write down parametric equations for this circle, where we have one equation for x and another equation for y, and both of them are going to be in terms of some parameter. And the parameter we tend to use in this case is this angle theta. On this unit circle, for any value of theta, we get a point whose x-coordinate and y-coordinate can both be expressed in terms of theta, namely, x is cosine theta and y is sine theta. And as theta runs through its values, this point traces out the curve, the circle. So we could say that the unit circle is the graph of this set of parametric equations. Of course, it is also the graph of the equation x squared plus y squared equals 1, and that's fine too. We often want different representations for the same thing. This gives a static picture of the circle all at once. Every point on the circle satisfies this equation. These parametric equations give us a more dynamic picture of the circle being traced out by a moving point as theta runs through a certain set of values. But in the general situation, we can think of a curve in the plane as being traced out by some moving point, and even though we might not have something nice like an angle with which to parametrize it, we can always think of the parameter t as representing time, which no doubt is why we tend to use t for it. So in this picture here, we might imagine that our bug crawling around on the window is at this point when t equals 0, and at this point when t equals 1, and at this point when t equals 2, and this point when t equals 3, and so on and so forth. And what we would like would be two formulas, one for each coordinate, so that at any given time, I can tell you the x-coordinate of the moving point and the y-coordinate of the moving point. So that if we would have something like x, meaning the x-coordinate of the moving point is some function of t, and y, meaning the y-coordinate of the moving point, is some other function of t. And these two equations would be our parametric equations for this curve. One very nice advantage of the parametric approach is that it generalizes to higher dimensions. For example, if we have a set of 3 parametric equations like this, where 3 variables, x, y, and z, are all functions of some parameter t, then I can imagine a situation like this, but in 3-dimensional space. I have my 3 coordinate axes now, and for every value of t, there's a corresponding point x, y, z in space. So maybe, for example, when t is 0, x is 1, y is 2, and z is 3, so that we get a point like this. 1 unit down the x-axis, 2 parallel to the y, and 3 parallel to z. And for other values of t, we would get different points in space. So as t is varying continuously, we can think of this point moving in space. This notion of a moving point is central to the idea of parametric equations. And I'd love to show you a good example, but graphing parametric equations is a hard enough problem even in 2 dimensions. Trying to do it in 3 dimensions is pretty hopeless, except in the simplest cases. So I'm going to need a little computer assistance here.
Okay, I have jumped onto GeoGebra to show you the graph of a set of 3 parametric equations, something that realistically we could never hope to graph by hand. But we know that for every value of t, there's an output point with coordinates x, y, z. And if we follow that moving point as t runs through its possible values, we should see it moving around in space. And here, in fact, it is. It's a little hard to see what it's doing. We can get a different perspective by moving this thing around a little bit. I changed the color as well. And if we are very careful, if we attach a pin to that point, we can trace the curve out, which ends up looking something like this. And now we can see the point moving around on that curve. Maybe I'll try to get an optimal perspective here. I don't know that there is one, but the red axis is the x-axis, the green axis is the y-axis, and the blue axis is the z-axis. So you can see that thing tracing out the curve as t runs through various values.
And now we will return to our regular broadcast. Okay, so parametric graphs can get pretty complicated. And I should mention, we don't just use them for geometric purposes. Parametric equations have obvious value in, say, physics, or we might be using them to model literally a moving point, or at least some moving object whose path we're interested in studying. And outside of both geometry and physics, they are commonly applied tools. An economist, for example, might be interested in tracking the S&P 500. 500 particular stocks. And if we're tracking those over time, when the clock starts at 0, which might be when the stock exchange opens on a given day, all 500 of those stocks have a particular value. Well, if I put them in some particular order, even if it's just alphabetical order, and I have here's the value of this stock, and here's the value of this stock, and here's the value of this stock, and I have all those values at the same moment in time, I can think of those 500 numbers as a point in some 500-dimensional space. And then I can look and see their prices, whatever, say an hour later. And we'll call that t equals 1. And then I would have a slightly different point in 500-dimensional space. And then the clock ticks again, and I have a different point in 500-dimensional space. And I might be interested in tracking how the values of those particular stocks change over time. And so I can think about that in an abstract way as some kind of curve winding its way through 500-dimensional space. And we can use the tools of parametric equations to study it. Well, we're not going to be doing quite that sort of thing in here. We would need some more tools at our disposal to really get the most out of parametric equations. We need to use vectors as well, which I'm not assuming for this class, though probably most people watching this have some experience with vectors. And when you take a course in multivariable calculus, you will dwell on those sorts of parametric equations much more. In this class, it will mostly be a matter of introducing the idea of parametric equations, and once we bring calculus into the picture, in the next section and the next video, parametric equations will help us understand from yet another angle how to think in terms of calculus, how to make use of that Leibniz notation in yet another setting. And we will mostly be sticking to parametric equations in R2, in two-dimensional space. In the section of the book corresponding to this video, I dwell a lot on one particular parametric curve called a cycloid, which hopefully you've read about already. I don't want to say any more about that here, other than the fact that it's parametrized in a rather unusual way.
After recording this, I changed my mind. I do want to say a few things about the cycloid here. Not too much, but enough to help you understand the derivation of its parametric equations that I give in the book. This is one place where a little GeoGebra animation can do wonders to help, I think. So first, just to be clear how the cycloid is generated, we have this circle sitting on the x-axis with the point of tangency at the origin. I've put one spot of red paint on the circle at that point. Now we're going to roll the circle down the x-axis and mentally follow the path that the red dot takes. So here it goes. And I'll bring it back. That arch that the point follows when we roll the circle is the cycloid. And if I put a little tracer on the point, we can actually see it here on GeoGebra, like this. And I hope that dynamic presentation gives you a better feel for how the cycloid is generated than just reading about it in the book. The next thing to grasp is what the angle is that we use as a parameter. That angle is probably easiest to understand as you are watching the wheel roll. So anyway, here it is. It's that green angle. That angle is going to be our parameter theta. And our parametric equations give the x and y coordinates of the moving point as functions of theta. Most of the derivation of those parametric equations in the book is pretty straightforward geometry, but there is one step that could throw you off. So I want to highlight that one step here. In the circle's initial position, only one of its points, that red one, has touched the x-axis so far. As it rolls, more and more of its points touch the x-axis. And what I'm going to do is I'm going to paint all those points green, so that if we watch the circle rolling, we might see something like this. And by the time we complete the cycloid, every point on the circle will be green. Okay, that's the first thing we'll use in our explanation. Next, instead of just painting the points on the circle that have touched the x-axis green, I'm also going to paint the points on the x-axis that have been touched by the circle green. So now I will have a green circular arc and a green line segment developing. And it should be clear that those two things will have the same length, even though one of them is curved and one of them is straight. The equality of those lengths is going to be crucial at one point in the derivation of the parametric equations for the cycloid. At that point in the derivation, we need the length of that line segment on the x-axis, but we can get it because we know the length of the circular arc by a basic formula from geometry is that angle theta times the radius, which in the book I have as a. So the circular arc is a theta, which means the line segment is a theta. Anyway, now that I have clarified at least these pieces of the derivation of the cycloid's parametric equations, I'm going to leave the rest of the derivation for you to follow in the book. I think you should be able to handle it now. So goodbye to GeoGebra.
It's an interesting curve, both intrinsically and for historical reasons, so I thought you'd have fun reading about it. Here, though, let's start to get a feel for these things by looking at a really simple set of parametric equations. These guys. Like any set of parametric equations, we can think about these as tracing out a curve in the plane where the x and y coordinates of some moving point are determined by the value of this parameter t. So let's see if we can get a feel for what this would look like. Well, what happens when the parameter t is 0? In that case, these terms are gone, and the moving point would be at 1, 2. And I've marked this here, t equals 0, just so we can keep track. What happens at some other value of t, say 1? Well, then x would be 1 plus 2, which is 3, and y would be 2 minus 1, which is 1. So now the moving point would be at this point. And a second later, so to speak, when t equals 2, what would happen? Well, now x would be 4 plus 1, which is 5, and y would be 2 minus 2, which is 0. So the point would be right here. And I hope you can see what's happening. Not just from the fact that we've plotted 3 points, that's not enough to go by, but that should give us insight to look back at this and say, oh, I see, every time the clock ticks, t increases by 1, this x value is just going to pick up an extra 2. An extra 2 gets tacked on. That's why I keep moving 2 to the right, 2 to the right. And every time the clock ticks, every time t moves forward by 1, I'm going to subtract off 1 from the y value, which is why I'm moving forward to the right by 2, but dropping down by 1. Moving forward 2, dropping down by 1. And once we've grasped that, we understand exactly what the graph would look like. it's a straight line. In fact, its slope will be -0.5, because for every 2 we run, we rise, so to speak, -1. So -1/2 would be the slope. And once we've recognized that the slope is -0.5, and of course we know some points on the line, like this one, 5, 0, we could write down the equation of the line in the usual way. Passes through 5, 0, the slope of -0.5, so we could go through the usual Algebra 1 motions to get the equation of this line in its typical form. But there are other ways we might have done it. For example, sometimes when we have a pair of parametric equations, we can come up with a corresponding Cartesian equation by playing with them in such a way that we can eliminate the parameter and get it into a single equation involving just x and y. In this case, for example, we might rewrite that second equation by solving for the parameter, in which case we get t is equal to 2 minus y. So now everywhere I have a t, I can replace it by an expression in terms of y. Now take that, substitute it into the first equation, and then instead of this relationship between x and t, I'll end up with a relationship directly between x and y. If we do that, we'll obtain this, which we now at least see is a linear equation in x and y. So if we hadn't been thinking geometrically, at this point we would recognize, this looks like it lies on a line in the plane. And it had better be the case that if we manipulate this a bit, we can get it into this form. Let's make sure. Distribute that 2 and we get this. Add those and we get this. Rearrange this and we get this. Divide both sides by 2 and we get this, which we can also rewrite as this, just like we said we would. This brings me to another point about parametric equations as opposed to Cartesian equations. A graph in the plane has a unique Cartesian equation, apart from little algebraic manipulations like we just did. Multiplying both sides by 2 or subtracting 97 from both sides, technically it gives us a different equation, but it's the same thing. You can manipulate one back into the other one. It's a different story with parametric equations. A graph does not have a unique representation in terms of parametric equations. I can get a different set of parametric equations for this same line that looks substantially different. For a real simple one, let's just imagine that instead of starting at this point, and then every second moving 2 to the right and 1 down, we were to start, say, at this point. And every time our parameter increases by 1, let's say we go back by 4 and go up 2. That will clearly give us the same line, only the moving point will be traversing it in the opposite direction, and in some sense, faster. The stuff up here would have positive values of our parameter, and when our parameter is negative, we would be back here. So if we wanted to do that, we could have something like, well, let's see, x would have to start at 5, and every second we said we were going to subtract off 4, and y would start at 0, so I won't write anything, and every second we were going to add on 2. And this would be a different set of parametric equations for the same graph. These both parametrize the same thing. In this case, we're starting here and going this way. In this case, we're starting here and going this way, twice as fast. And these aren't obviously the same thing from an algebraic perspective until you recognize the geometry underneath each one. And it doesn't even have to be linear equations like this. We could have something like these, where I've got these t cubeds in there. When t is 0, those are wiped out, and I start at 3, 1, this point. When t equals 1, well, we move another 8 down the road this way, and drop 4, which of course puts us back on that line. When t equals 2, we move really far down the road in the next second, because we have to cube that 2 to get 8, and so we're actually adding on 64 from where we started. And here we're dropping 32 from where we started. But that'll still put us back on the line, because from every 2 we're going over, we're dropping 1. It's just that the point is going to start moving really fast. It's not moving at a steady pace the way it was here or there. And again, for negative values of t, we would be going the opposite direction, and increasingly fast as we go. So by playing around with the equations, you can change the direction in which the curve is traversed. You can change the speed at which it moves, and all sorts of things like that. A little while ago, I showed how you could eliminate the parameter t in these parametric equations and come up with a single equation just in x and y, which in this case, of course, was the equation of that line. That was easy in this case because both the parametric equations were linear, but in general, the strategy of solving one equation for the parameter and then injecting it into the other one, while it will work in theory, can be tricky in practice. Now, truth be told, we generally don't need to do that. If we're working with parametric equations, we are usually doing so for a reason and don't want to convert over to a Cartesian equation. But I still want to point out that there are certain cases where you can do that, and you are generally best able to do it not by the trick we used there of explicitly getting the parameter as a function of one variable and substituting into the other, but rather just by combining the two equations in an interesting way, a way that takes advantage of things you already know. For example, let's look at this set of parametric equations. We know that if x were cosine t and y were just plain old sine t, then what we would have was the parametric equations for the unit circle. And as a result, we would know that all points on the graph of this set of parametric equations would in fact be solutions to x squared plus y squared equals 1, since that is the Cartesian equation for the unit circle. Well, if only, if only. This isn't just y equals sine t. So I can't just say, oh, that's the same thing as x squared plus y squared equals 1. It isn't. But it's so close. Can't we just make some little adjustments? Well, yes. We wish that y were just sine t. It isn't. But something related to y is just sine t. Namely, y plus 3 all divided by 2. Adding 3 to this and dividing it by 2 leaves you with just sine t. And I know that if I square sine t for any t, and I add the square of cosine t, which in this case is just x, then I've got secretly underneath here cosine squared plus sine squared, and I know by the Pythagorean identity that is always 1. So I'm effectively done. We have come up with a Cartesian equation corresponding to these parametric equations. Every point on their graph also lies on this graph. And by the way, what does the graph of this thing look like? That would be nice to know because it's not obvious what the graph of this looks like. So maybe if we could figure it out over here, that would tell us something about the graph of our parametric equations. Again, this looks so close to the equation of the unit circle that our first thought should be, well, look, I know what the graph of this looks like. It's the unit circle. So maybe by thinking about the algebraic transformations that get me from this equation to this one, I will understand the geometric transformations that will get me from this graph to whatever the graph is that I'm actually looking at. That sounds plausible, and it's a standard pre-calculus topic, so we should be able to do that, right? How do I get from here to here? I claim we can do that in 2 easy algebraic transformations. First, let's substitute y over 2 for y. That'll get me part of the way there, leaving me with this equation. Well, what geometric transformation corresponds to this algebraic transformation? If you substitute y over 2 for y, everywhere y appears in an equation, what happens geometrically to the graph? That's a vertical stretch of the graph by a factor of 2, because any coordinate pair, x, y, that satisfied this equation isn't going to work here anymore. This is going to be too small now, because the y-coordinate is being cut in half. So you have to double all the y-coordinates to satisfy this equation. That means all the y-coordinates in our original graph must get doubled, which is where we get that vertical stretch by a factor of 2. So we'd end up with a graph for this equation that looks like this. This goes out to 2 vertically, but still only 1 horizontally. Instead of a circle, we have a stretched circle, better known as an ellipse. Excellent, but we're still not quite at our target equation. What transformation of this could I do to get up to this one? Well, that's easy. I just substitute y plus 3 for y, turning this into that. Well, what does that do geometrically? What geometric transformation corresponds to this algebraic transformation of substituting y plus 3 for y? Well, you know that one. It's going to be a vertical shift down by 3 units, because any coordinate pair that satisfied this equation, any pair xy, isn't going to satisfy this one because of this plus 3 unless you first subtract 3 away from its y coordinate. If you do that to every point, that satisfies this, in other words, every point on this ellipse, is going to pull the ellipse down by 3 units so that it looks like this. And that's that. So we very quickly came up with a Cartesian equation corresponding to these parametric equations. And then by thinking about it in terms of some simple pre-calculus transformations, we were able to figure out what the graph of this thing looked like, namely this ellipse. So we did better than just coming up with that equation. We were able to see what curve the moving point was tracing out. And we got to review some important ideas from pre-calculus too. Good. Speaking of ellipses, I want to show you one last interesting set of parametric equations. Or rather, I want to lead you to one last set of parametric equations by starting with a geometric problem. Suppose we have a couple of concentric circles centered at the origin. Now imagine I've got my usual rotating ray going around as theta varies from 0 to 2 pi. And in every possible position for that ray, I'm going to look at the points where it cuts the two concentric circles. From those points, I'm going to draw lines parallel to the axes, like this, and the place where they intersect, I'm going to get a new point, which I'll put in red. And I do that at every position of the ray. Here, for example, I get these points on the circle, draw those parallels in, and I get a point like this. And here's another one, and another, and a couple more, and you get the idea. If you think about this for a little bit, you'll see that we should end up with something like this. The set of all points that come out of that construction for all positions of the rotating ray. Then we have this interesting sort of cat's eye drawing here. And it looks like this curve might be an ellipse. Maybe, maybe not. I mean, it has that kind of general shape, but an ellipse is a delicately defined thing. Is this really a stretched version of that circle, or is it just something close to it? Well, we can find out by coming up with the Cartesian equation for this thing and see if it matches the equation of an ellipse. And the way I'm going to do that is to actually parametrize it, to come up with a set of parametric equations for it, which we can then convert to a Cartesian equation. This is now far too cluttered to work with. I want to just concentrate on a single point being generated. Something like this. Now there's a pretty obvious candidate here that we can use for a parameter. We generated each point by rotating a ray through a certain angle. So let's call that angle theta, and we are going to try to come up with the x and y coordinates of this point that gets generated by this angle. And if we can do that, then we will have our parametric equations. So let's get started. Actually, one thing we will need to specify will be the radii of our two circles, since those will obviously have an effect on where this point lives. Let's call the big one A and the little one B. And I claim that we already have enough information to write down our parametric equations very easily. These will give us the x and y coordinates of this red point. Let's start with the y coordinate, which is probably the simpler of the two, though they're both pretty simple. We want the y coordinate. Well, that's this length right here that I've just put in blue, which in turn, of course, is obviously equal to this length that I'm also putting in blue. But what's that? Well, that's a leg of a right triangle. This right triangle, whose hypotenuse is the radius of the little circle, namely b. So by the most basic right angle trigonometry, this length is going to be b times the sine of theta. But that length is that length, which is the y coordinate of that point. So y is going to be b sine theta. Well, that was easy. How about the x coordinate of this point? Well, that's this length right here that I'm putting in green. And hey, that's the leg of another right triangle. And I know the hypotenuse of that triangle. It's the radius of the big circle, which we've said is A. So again, by the simplest of right angle trigonometry, the green leg of the highlighted triangle is going to be A times the cosine of theta. So that length, the x coordinate of this point, gives us our other parametric equation. X is equal to A cosine theta. And we have our parametric equations. If you stick these into your favorite graphing program, you won't see these two circles, but you will in fact get this curve we were talking about a moment ago. But back to our question, is it an ellipse? Well, let's see. Let's play with these. If we can put them into a Cartesian form, we might recognize it as the equation of an ellipse. Let's find out. How are we going to do that? Hey, I've got an idea. Let's use that trick we used before. We've got this cosine here and this sine here. Ooh, if only those pesky a's and b's were gone, then we could just say that x squared plus y squared is 1. Still, we can make some easy algebraic adjustments. From this, we see that if we took x and divided by a, we'd just be left with cosine. And if we took y and divided by b, well, we'd just be left with sine. So we've got cosine and sine. Well, everybody knows that if you square those guys and add them together, cosine squared plus sine squared is 1 by the Pythagorean identity. So every point on the graph of this set of parametric equations lies on the graph of this Cartesian equation. And this is indeed the equation of an ellipse. If you didn't recognize that immediately, you should by thinking about transformations. You know what the graph of this looks like, that's the unit circle, and you can get from here to here with 2 algebraic transformations. Normally I wouldn't write this all out, but just for you. If we substitute x over a for x in this, we get this equation. What's the corresponding geometric transformation that this graph undergoes? Well, that's going to be a horizontal stretch by a factor of a. Points that satisfy this no longer satisfy this equation. To satisfy this, we would have to take a point that satisfies this and multiply its x-coordinate by a, so that when it gets divided out here, everything still balances out. So multiplying all the x-coordinates by a stretches this thing horizontally. It might compress it if a is less than 1, and we'd end up with a picture something like this. It's literally a stretched circle, so this is an ellipse that goes out a in the x direction and only 1 in the y direction. Now, how do I get from here to here? Of course, we substitute y over b for y, turning this into this. And what's the geometric transformation that corresponds to that algebraic one? Well, that's going to be a vertical stretch by a factor of b. So instead of having an ellipse that goes out a in the x direction and 1 in the y direction, now it's going to go out a in the x direction and b in the y direction, which is what we had in our original picture. We started with a circle, the unit circle, we stretched it twice, and we end up with this. So this curve that we generated in that interesting manner, it truly is an ellipse. Well, all right, I think that's enough for the pre-calculus side of parametric equations. We will solve some calculus problems with parametric equations next time. And at the same time, we'll be using parametric equations to help us gain a deeper understanding of calculus.